In the multiple choice, you are not allowed to use your calculator, but you can use your data booklet. And I've got the page for the first unit of the data booklet here available, so we'll look at that from time to time. So it says a volume is measured to be 52 millimeters cubed. The volume in meters cubed is. Now, if you go from a millimeter to a meter, this milli over here means 1,000. So that means 10 to the minus 3. So when I go from millimeters to a meter, I actually got to divide by 1,000 or times by 10 to the minus 3. Now if I'm going from millimeters cubed to meters cubed, I've got to take this 10 to the minus 3 and I've got to multiply it by 10 to the minus 3 and multiply it by 10 to the minus 3. So I've got to do that 3 times. So that's actually 10 to the minus 9. So I'm going to have 52 times 10 to the minus 9 meters. So you've got to be quite careful with that when you go to area and when you go to volume. Now obviously here this is going to be my correct answer. D will be the correct answer because I can make this 52.5.2 times 10 to the negative 8 meters cubed. Question 2, we have here the masses and weights of different objects are independently measured. The graph is a plot of the weight versus mass that includes error bars. These experimental results suggest that, and we can look at these over here. Now, just the idea, a systematic error is usually an error caused by a fault in the measuring device, and it sends the result a certain amount off, but the same amount off. So that's your systematic error. A random error is in all different directions. Now, if it was random, we would expect that we would get something like this forming. It would be all over, but we're not getting that. We're getting it pretty much in a straight line, which we would expect, because we know that the weight is equal to mass times g, so we would expect this to be a straight line. This is a proportional graph. We would expect this graph to go through the origin and a straight line, although I have not drawn it as that, so it would be a straight line through the origin like that. Now this over here is a straight line, but it's not going through the origin. You see it's off here, so there is the same amount that's off, and that would be a systematic error. So A is the correct answer. Measurements show a significant systematic error but small random error. So it forms a straight line. All the line crosses all the points, but they are all being shifted up slightly. They've all moved up a certain amount. All of these have moved up a certain amount. Question 3. The magnitude of the mass of the universe is of the order. Now, when we talk about order, we're talking about a 10 to the power of something. Now, you need to know these values, and it's of the order of 10 to the 50. This one over here, 10 to the 50, that is the mass of the universe. Some of them you can work out. We're going to question 5, we will actually calculate a bit. Question 4, which of the following is a valid statement? We have a measurement that is not precise can be accurate. Can be, so there's a possibility. So you may have, this is your value, and you may have all your values there like that. But when you take the average of them, you get it pretty much accurate results, but they are not precise because they are spread out. A measurement that is precise is always accurate. That's not true, because you can have your actual value there, but you can have all your results all over here. See, very precise, but not on the actual accurate value. So the always takes that out. A measurement that is not precise will always be inaccurate. That is not true. And repeated measurements will always increase accuracy and precision. Not always. It all depends how those repeated measurements are done. So it's the always here that make these B, C, and D not correct, but it's the can be accurate here that makes this one the most likely answer. Question 5. The time elapsed since the beginning of the universe is of the order. Now, the universe is about 13 billion years old. It's about 13.4. So let's just see what that is in an order in seconds. So that's 13 billion. We can write as 10 to the 9. So that's 13 times 10 to the 9 years. And we know in each year there's 365 days, and there's 24 hours, and there's 60 minutes, and there's 60 seconds. Now let's put these into a 10 to the power. This we could write as 10 to the power of 1 times 10 to the power of 9 times this, because it's less than 500, would be 10 to the power of 2. 24 we can write as 10 to the power of 1. We're just approximating here. 60, it's closer to 100, so it's 10 to the power of 2 times 10 to the power of 2. So there we've approximated this. Now we just add our exponents. It's 1, 10, 12, 13, 15, 17. So we about 10 to the 17 around about, and we can see the closest one to that is 10 to the power of 18. So it's B over here. You can see that these are all, that's the closest possible one. Question 6. In an experiment to measure the acceleration of free fall at the surface of the Earth, the following results were obtained. The results are accurate and precise. Well, we know that the actual value is 9.81 around. So we can't really say that these are accurate, but we can say they're precise because they're very close to each other. You can see this, there's a difference here of a 0.02. That's the maximum difference. So we can say that, we can't say it's accurate, so that's not right, but we can say inaccurate but precise. B would be correct. Accurate, no, definitely not. Inaccurate and imprecise, no, because they are pretty precise. 7. The best estimate for the time it takes to cross the nucleus of a hydrogen atom. This is 10 to the minus 23. Now, you should probably know that. I mean, the size of a regular atom is about 10 to the minus 10 meters. So if we looked at the time it goes to cross an atom, we know that velocity is equal to distance over time. Time is equal to distance, 10 to the minus 10, divided by our velocity, which is 3 times 10 to the 8. So we're looking at here at about an approximate value of about 10 to the minus 19 seconds to cross an atom. But the nucleus is very small, and we're talking about a hydrogen atom. So the nucleus, when we're actually talking about the diameter of a proton, is very, very small. So I mean, the likelihood, the two possible values that are really possible here are these two. 10 to the minus 23 and 10 to the minus 20. But your nucleus is about you could say at least 1/10,000th of the size of an atom. So this is the one that is correct, is 10 to the minus 23. And for question 8, we have the length of each side of a sugar cube is measured as 10 millimeters with an uncertainty of plus minus 2 millimeters. Which of the following is the absolute uncertainty in the volume of the sugar cube? Now to do this, I'm just going to bring up this formula over here. We're going to use this formula when you get in multiplication, because I know that volume is equal to my length cubed, like that. So if I put it into this formula, this over here is my absolute uncertainty and this is my value. Now, because it's 10 millimeters, the volume is actually equal to be 10 times 10 times 10, which is equal to 1,000 millimeters cubed. That's the volume. But in each case, we've got an uncertainty of 2 millimeters. So in putting that into the formula, I'm going to have that my absolute uncertainty in my volume divided by my volume is equal to the absolute uncertainty of my length, which is 2 divided by 10, and I'm going to have 3 of those because it's 10 times 10 times 10, so it's plus 2 over 10 plus 2 over 10, or 3 times 2 over 10. So when you add that together, we get 6 over 10. Now my volume here, my volume is 1,000. So my absolute error in my volume is going to be 1,000 times that, which is 600 millimeters cubed value. So it's going to be D, plus minus 600 millimeters cubed.